Hello students, welcome to my first class on software project management. The subject is extension to the software engineering. Software project management is completely a theory subject. The first topic is conventional software management. Conventional software management practices are sound in theory, but practice is still tied to outdated technology and techniques. Conventional software economics provides a benchmark of performance for conventional software management principles. The best thing about software is it is flexible, it can be programmed to do almost anything. Yes, the best thing about the software is you can do anything. The worst thing about the software is it is also a flexibility. The almost anything character has made it difficult to plan, monitors and controls software development. Three important analyses of the state of the software engineering industry are: first, software development is still highly unpredictable. Only about 10% of software projects are delivered successfully within initial budget and schedule estimates. Management discipline is more of discriminator in success or failure than our technology advances. The level of software scrap and rework is indicative of an immature process. All three analyses reached the same general conclusion. The success rate for software project is very low. The three analyses provide a good introduction to the magnitude of the software problem and the current norms for conventional software management performance. So the main 3 points are: software development is still highly unpredictable, management discipline is more discriminatory in success, the level of software scrap and rework is indicative. The waterfall model. As today is the first class, I am giving the basic details. Most of software engineering tests presents the waterfall model as the source of conventional software process. It provides an insightful and concise summary of conventional software management. Three main primary points are: there are two essential steps common to the development of computer programs: analysis and coding. The two basic steps in a building program. In order to manage and control all of the intellectual freedom associated with software development, and one must introduce several other overhead steps, including system requirements definition, software requirements definition, program design and testing. These steps supplements the analysis and coding steps. Below figure illustrates. Figure means the same figure of the first step is analysis, coding, requirements, analysis, design, testing, operation. Profile and the basic steps in the developing a large scale program. The basic framework described in the waterfall model is risky and invites failure. The testing phase that occurs at the end of the development cycle, the first event for which timing, storage, output, input transfers are experienced as distinguished from analyzed, the resulting design changes are likely to be so disruptive that the software requirements upon which the design is based are likely violated. Either the requirements must be modified or a substantial design change is warranted. This is all about waterfall model, and few points in this waterfall model are: program design comes first. Insert a preliminary program design phase between the software requirements generation phase and the analysis phase. By this technique, the program designer assures that the software will not fail because of storage, timing, and data flux continuous change. As analysis proceeds in the succeeding phase, the program designers must impose on the analyst the storage, timing, and operational constraints in such a way that he senses the consequences. If the total resources to be applied are insufficient, or if the embryonic, that means in an early stage of development, operational design is wrong, it will be recognized at its early stage, and the iteration with requirements and preliminary design can be redone before final design, coding, and testing commences. How is this program design procedure implemented? The following steps are required. Begin the design process with program designers, not analysts or programmers. Design, define, and allocate the data processing models even at the risk of being wrong. Allocate processing functions, design the database, allocate execution time, define interfaces and processing modes with the operating system, describe input and output processing, and define preliminary operating procedures. To write an overview document that is understandable, informative, and current, so that every worker on the project can gain an elemental understanding of the system. Documenting the design. The amount of documentation required on most software programs is quite a lot, certainly much more than most programmers, analysts, or programmers, designers are willing to do if left to their own devices. Why do we need such documentation? Each designer must communicate with interfacing designers, managers, and possibly customers. During early phases, the documentation is the design. The real monetary value of documentation is to support later modifications by a separate test team, a separate maintenance team, and operations personnel who are not software literate. We have to do it twice. If a computer program is being developed for the first time, arrange matters so that the version finally delivered to the customer for operational deployment is actually the second version insofar as critical design operations are concerned. Note that this is simply the entire process done in miniature to a time scale that is relatively small with respect to the overall effort. In the first version, the team must have special broad competence where they can quickly sense trouble spots in the design, model alternatives, forget the straightforward aspects of the design that are not worth studying at this early point, and finally arrive at error-free program. plan, control. This is all we are just recapping the old topics. Error-free programs, the control and monitor testings. Without question, the biggest user of project resources, manpower, computer time, and management judgment is the test phase. This is the phase of greatest risk in terms of cost and schedule. It occurs at the latest point in the schedule when backup alternatives are least available, if at all. The previous three recommendations were all aimed at uncovering and solving problems before entering into the test phase. However, even after doing these things, there is still a test phase, and there are still important things to be done, including employ a team test specialist who were not responsible for the original design, employ visual inspections to spot obvious errors like dropped minus signs, missing factors of two jumps to wrong addresses. Do not use the computer to detect this kind of thing. It is too expensive. Test every logic path. Employ the final checkout on the target computers. Involve the customers. It is important to involve the customer in a final way so that he has to committed himself at earlier points before final delivery. There are 3 points following requirements: definition, where the insight, judgment, and commitment of the customer can bolster the development effort. These include a preliminary software review following the preliminary program design step, a sequence of critical software design reviews during program design, and a final software acceptance review. The waterfall model in practice, some software projects still practices the conventional software management approach. It is useful to summarize the characteristics of the conventional process as it has typically been applied, which is not necessary as it was intended. Projects destined for trouble frequently exhibit some symptoms like protracted integrations and late design breakage, late risk resolution, requirements driven functional decomposition, adverse stakeholder relationships, focus on documents and review meetings, and protracted integration and late design breakage. For a typical development project that used a waterfall model management process, we can illustrate development progress versus time. Progress is defined as percent coded, that is demonstrable in its target form. The common sequences were early success via paper designs and through briefings, commitment to the code late in the life cycle, integration nightmares due to unforeseen implementation issues and interface ambiguities, heavy budget and schedule pressure to get the system working, late shoe homing off, no optional fixes with no time for redesign, a very fragile and unmentionable product delivered late. And few points in this waterfall model are: in the conventional model, the entire system was designed on paper, then implemented all at once. Then integrated provides the typical profile of complex expenditures. Requirements driven functionality decomposition. This approach depends on specifying requirements completely and ambiguously before other development activities begin. It naively treats all the requirements as equally important and depends on those requirements remaining constant over the software development life cycle. These conditions rarely occur in the real world. Specification of requirements is a difficult and important part of the software development process. Another property of the conventional approach is that the requirements were typically specified in a functional manner. Built into the classic waterfall process was fundamental assumption that the software itself was decomposed into functions. Requirements were then allocated to the resulting components. This decomposition was very often very different from the decompositions based on object oriented design and the use of existing components. We can illustrate the result of requirement driven approaches, a software structure that is organized around the requirements of specification structure. And we have to maintain stakeholder relationships, but there are some adversarial things. The conventional process tended to result in adversarial stakeholder relationships, in large part because of the difficulties of requirement specification and the exchange of information solely through paper documents that captured engineering information in ad hoc formats. The following sequence of events was typical for most contractual software efforts. The contractor prepared a draft contractor deliverable document that captured an intermediate artifact and delivered it to the customer for approval. The customer was expected to provide comments. The contractor incorporated these comments and submitted final version of approval. This one-shot review process encouraged high levels of sensitivity on the part of customers and contractors. And we have to focus on the documents and review meetings also. The conventional process focus on the producing various documents that attempted to describe the software product with insufficient focus on producing tangible increments of the products themselves. Contractors were driven to produce literally tons of paper to meet milestones and demonstrate progress to stakeholders rather than spend their energy on tasks that would reduce risk and produce quality software. Typically, presenters and the audience review the simple things that they understand rather than complex and important issues. Most design reviews therefore resulted in low engineering value and high cost in terms of the effort and schedule involved in their preparation and conduct. They presented merely a facade of progress. Conventional software management performance. Barry Boehm best scientist in software engineering, industrial software metrics top 10 list is a good objective characterization of the state of software development. Finding and fixing a software problem after delivery costs 100 times more than finding and fixing the problem in early design phases. You can compress the software development schedule 25% of nominal but no more. For every $1 you spend on development, you will spend $2 on maintenance. That means $1, $2. Software development and maintenance costs are primarily function of the number of source lines, of course. Variations among the people account for the biggest difference in software productivity. The overall ratio of software to hardware costs still growing. In 1955 it was 15 into 85, but in nowadays 85 into 15. Only about 15% of the software development effort is devoted to programming. Software systems and products typically cost 3 times as much per software development life cycle as individual software programs. Software system products times as much. Walkthrough catches 60% of the errors. 80% of the contributions comes from 20% of the contributors. Software economics, this is also a vast topic. Most software cost models can be abstracted into a function of 5 basic parameters: size, process, personnel, environment, and required quality. The size of the end product, which is typically quantified in terms of the number of source instructions or the number of function points required to develop the required functionality. The process used to produce the end product, in particular the ability of the process to avoid non-value adding activities, rework, bureaucratic delays, communications overhead. The capabilities of software engineering personnel, and particularly their experience with the computer science issues, the applications domain issues of the project. The environment, which is made up of tools and techniques available to support efficient software development and to automate the process. The required quality of the product, including its features, performance, reliability, adaptability. The relationships among the parameters and the estimated cost can be said as effort equal to personnel into environment into quality into size of the process. Effort is equal to personnel into environment into quality into size of the process. One important aspect of the economics as represented within today's software is cost models is that the relationship between effort and size exhibits a diseconomy of scale. This diseconomy of scale of software development is a result of the process exponents being greater than 1. Contrary to most manufacturing processes, the more software you build, the more expensive it is per unit item. Generations of basic technology advancements in tools, components, and processes, the required levels of quality, personnel assumed to be contrast. The ordinate of graph refers to software unit costs realized by an organization. The 3 generations of software development life cycles are conventional, transition, and modern practices. Let me explain about what is a conventional, transition, and modern practices. In between 1960s to 1970, craftsmanship organizations used custom tools, custom processes, and virtually all custom components built in primitive languages. Project performance was highly predictable in that cost, schedule, and quality objectives were almost always underachieved. And our transition in 1980s to 1990s, software engineering organizations used more repeatable processes and off-the-shelf tools. The mostly, that means greater than 70% of the components built in high-level languages. Some of the components, less than 30%, were available as commercial products, including the operating system, database management system, networking, and graphical user interfaces. Modern practices. After 2000, the later software production, this book's philosophy is rooted in the use of managed and measured process of integrated automations environments, and mostly 70% of the off-the-shelf components, perhaps as few as 30% of the components, need to be custom built. Technologies for environment automation, size reduction, and process environment are not independent of one another in each era. The key is a complementary growth in all technologies. For example, the process advances could not be used successfully without new component technologies and increased tool automation. Organizations are Organizations are achieving better economies of scale in successive technology eras with very large projects, systems of systems, long-lived products, and lines of business compromising multiple similar projects. Provides an overview of how a return investment profile can be achieved in subsequent efforts across life cycle of various domains. And for the coming 3 to 4 minutes, let us discuss about cost estimation. Fully I can cover in the next class. This is also called as pragmatic software cost estimation. One critical problem in software cost estimation is lack of well-documented case studies of projects that used an iterative development approach. Software industry has inconsistently defined metrics or atomic units of measure. The data from actual projects are highly suspect in terms of consistency and compatibility. It is hard enough to collect a homogeneous set of projects that within one organization. It is extremely difficult to homogenize data across different organizations with the different process, languages, domains, and so on. There have been many debates among the developers and vendors of the software cost estimation models and tools. Three topics of these debates are of particular interest are which cost estimation model to use, whether to measure software size in source of lines of code or function points, what constitutes a good estimate. There are several popular cost estimation model: COCOMO model, checkpoint model, Estimax, Knowledge Plan, Prices, ProQMS, SEER, Slim, Softcast, SPQR by 20. COCOMO is popular model and well-documented cost estimation model. The general accuracy of conventional cost model is COCOMO. Most real-world use of cost model is bottom-up, substantiating a target cost rather than top-down should cost. The software project manager defines the target cost of software and then manipulates the parameters and sizing until the target cost can be justified. The rationale for the target cost may be to win proposal, to solicit customer funding, to attain internal corporate funding, or to achieve some other goal. The process described is not at all bad. In fact, it is absolutely necessary to analyze the cost risks and understand the sensitives and trade-offs objectively. It forces the software project manager to examine the risk associated with the achieving. So tomorrow we will discuss about cost estimation models clearly. Thank you.